Okay, so good morning, everyone. Can you all confirm you can hear me, right? Okay, so I want to welcome you to another statistical learning class. Of course, just to say the materials for the week have already been uploaded. Um, and let me also say this, I'm going to release the first assignment today because I think I want to make sure I teach one more concept before releasing that so that way I'm going to have enough. Okay, so assessing model accuracy in statistical learning. Now, let me prepare your mind. What are we trying to do today? Of course, what we're trying to do is I showed you the other time, if I if we want to study relationship or we want to make a prediction or we actually want to make an inference about why, okay, given some features, the whole thing is going to start from y equal fx plus the error. So the whole thing is going to start from model specification. Okay, so when we have a model specification, of course, we want to have a way to estimate the deterministic part of the model, which we call the function, and how are we going to know whether we've done a great job or not is what we want to do today, which we call assessing model accuracy in statistical learning. Of course, the other time, I think I started this on Friday, where I show you how we make use of mean-square error. But let me tell you this, to be able to know the appropriate model accuracy, the appropriate way of assessing the accuracy of your model, okay, you need to first answer some questions, okay, which is actually going to be our focus today. So in the outline, today I'm going to talk about the purpose of modeling, because for you to be able to know, uh, you know, the criteria that work, then we need to first know what your intention is, whether you want to explain or you want to predict. Because the metric of evaluation that we use in model explanation is different from the one that we use in model prediction. And that's why we want to know your intention. Okay, I'm going to discuss that. I'm going to make a distinction today between explanation and prediction. They are not the same. If you use um metric of evaluation for model explanation, okay, maybe you use a metric of evaluation for model explanation for model prediction, then you're getting it wrong. Or you're using metric of evaluation for model prediction for model explanation, you're also getting it wrong. Okay, so I'm also going to discuss something, the difference between model fitness and model complexity and the combination of the two. One, model fitness, the other one, model complexity, the other one, the combination of the two. Then after that, we're going to talk about prediction accuracy. If I want to talk about prediction accuracy, definitely I'm actually going to be biased towards prediction, telling the world my intention is prediction. Okay? Now, I want us to listen attentively because we don't we don't want a situation where you're actually going to end up using inappropriate metric of evaluation. It's synonymous with somebody who goes to a wrong court. Okay, when you are using a wrong metric of evaluation, it's synonymous with going to a wrong court. When somebody go to a wrong court, there's possibility that it's not going to get justice. Okay, Now, because of that, we need to be able to know our intention if we really want to know the appropriate metric of evaluation that's actually going to work. Now, if you take a look at the model that I have here, okay, if my intention is to make a prediction, the way it's going to be approached, okay, is going to be different from when my intention is to explain. There's a difference between explaining and predicting. The two are not the same. If the two are not the same, okay, then we actually going to have different metric of evaluation assessing the adequacy of the model or the algorithm. Okay, initially it was argued out, okay, around 1940s that, you know, um, the model explanation, maybe variation around model explanation and model prediction are equivalent. That person said that without uh, putting across, without putting forward any empirical evidence. He just said that. Okay. And there been a lot of debate upon debate, and I'm going to tell you it took um, community. I'm going to say the brilliant people in the research community, particularly scientific community, several years to realize, the two are not the same. And why is it that the two, if you take a look at what I'm having now, why statistical explanatory modeling differ from predictive modeling is because they are attacking different goals. That's why they are not the same. They are attacking different goals. The statistical explanatory modeling actually want to test a causal hypothesis. Okay, want to test a causal hypothesis. Okay, statistical explanatory goal actually is looking at the effect of a particular variable on a response. What is the effect? Looking at effect of a variable on a response is different from making a prediction. Does that make sense? Okay. And if a statistician is going to do that, or economists or psychologists, if they're actually um, going to do that, okay, uh, what they're going to do, since they want to explain, they will take a sample randomly from a target population, and whatever generalization they're going to make will be on the population from which the sample was choosing. That's what we call statistical inference. Okay. But in predictive modeling, okay, that's why I'm saying this. Okay. In predictive modeling, okay, we are not generalizing sample on the entire population, but you know what we want to do? We actually want to predict a new observation that was not even part of the population from which the sample was choosing. I'm going to say that again. There's a distinction between, okay, statistical explanatory model and a predictive model. Okay, the distinction is that in statistical explanatory model, modeling, we choose a sample from a target population, and the generalization will be on the entire population from which the sample was choosing. But in the predictive modeling, on the other hand, we want to generalize not to the entire population, but to a new observation that was not part of the population from which the sample was choosing. The two are not the same. Now, if your goal is to explain, okay, explaining the world is different from predicting the world. I'm going to say that again. Explaining the world is different from predicting the world. Now, if I want to explain the word, if I want to, if my intention is to explain, I'm actually going to use an explanatory model. Explanatory model will test or quantify causal effects, okay, for average record. And that's why whenever we're dealing with the explanation in statistics, we normally focus on average. Average this, average that. Does that make sense? But when it comes to predictive model, okay, we want to predict new observation, predicting new observation. And that is the reason why, if you understand your intention, you're actually going to be able to, you'll be able to know the appropriate metric of evaluation that you're actually going to use to assess the adequacy of your model. Now, because of that, to be able to shed more light on, on the difference between prediction and explanation, we got some tensions that I'm actually going to talk about. The theory versus data, causation versus association, retrospective versus prospective, or individual versus average record, and bias versus variance. Okay, these five we distinguish between tensions in explaining or predicting. I want to start with the theory versus data. Now, let me tell you this. If you take a look at this model, okay, the way we focus on the functionaries when the intention is explanatory, when we are seeking an explanatory goal, is different from the way we focus on it when we are dealing with a predicted goal. But let me tell you this. Before I go into the function, you know, when you are when you are pursuing an explanatory goal, the emphasis is going to be more on the theory. And that's why statisticians emphasize more on theory, physics on theory, chemists on theory, economists on theory, psychologists on theory, sociology on theory. Most of, in the scientific community, they have their theory. And the moment they have their theory, the only thing they want to do, they want to test hypotheses about the theory. And that is the reason if they're actually going to use explanatory model, and the F, this guy now, the function F is going to be constructed in such a way that support interpreting the estimated relationship between the features and the outcome. Explanatory goal is about studying relationship. It's about studying the effect of this variable on the other variable. That is the way the function F will be constructed. And in the predictive goal, when you are pursuing a predictive goal, okay, and you're actually going to use a predictive model, the way we construct F, the way we construct function F is different from the way it's going to be constructed when we're seeking explanatory goal. And that was why I said, okay, F is often constructed from the data. Okay, F is constructed from the data, and direct interpretability in terms of relationship between X and Y is not required. They are not interested in that. They are not interested in what is the effect of this on that. They are not interested, but what they are interested in, what is our, the appropriate combination of features that I'm actually going to combine that will give me the best prediction. That is what they care about. And of course, the emphasis when you are using a predictive modeling, the emphasis is more on data, not on the theory. They're only going to use theory in a less formal way, but the emphasis is going to be more on data. When you are pursuing an explanatory goal, the emphasis is going to be on theory. When you are pursuing an explanatory goal, more emphasis on theory, you are only using data as a spice or a supplement. Now, I want to go into causation and association. Okay, we all know, when relationship exists between two variables, that doesn't imply causation. Association does not imply causation. Okay, so in explanatory modeling, F represents an underlying causal function, and there's going to be an assumption that S is assumed to cause Y. And that is what you want to test. You stated that from day one. You have an assumption. Maybe you review literature and you found out a connection between X and Y. And you now want to test that statistically by conducting hypothesis testing. And when you are doing that, you're actually going to that's where you're going to see p-values. You're going to generate p-values to be able to take decision regarding how significant is the feature. But in the predictive modeling, okay, the function F will only capture association. It's not going to capture causation, only association. Okay, does that make sense? Okay, now the next in the tension is retrospective versus prospective. Okay, when you are pursuing an explanatory goal, okay, because you want to explain, okay, then what we normally do is to go backward. That is retrospective, because you actually want to go backward to be able to trace what happened in the past. Okay, you want to have an understanding. You need to have an understanding before explaining. Does that make sense? So when you, when we are pursuing an explanatory goal, it is retrospective. Okay, and that very F, okay, is used to test, okay, already existing set of hypotheses. You're actually putting forward a function, okay, and that very you put that forward because you want to test already hypothesis. You have some hypotheses that you have generated, probably based on research questions and so on like that. Okay, when you are pursuing an explanatory goal, is moving backward. Does that make sense? But if your focus is on if you are actually going for, maybe you're seeking a predictive goal, okay, it is prospective, moving forward. Don't forget, we want to predict new observation. We're not interested in the existing observation. We're focusing on new observation, and that will require us looking forward. Does that make sense? Predictive is about looking forward. Explanation is about looking backward. And that was why I said, okay, it's prospective, forward looking, in that F is constructed for predicting new observation. F you construct for predicting new observation is different from F that you construct in testing existing hypothesis. They are not the same. If they are not the same in terms of the way they are constructed, if you want to evaluate them, if you want to determine how adequate they are, they're actually going to have a different way to assess them. And that's why I'm bringing in this topic. You need to first understand what is your intention before you think about ways of assessing the adequacy of your model. The next in the line, individual versus average. Okay, whenever you are explaining, don't forget, whenever you are explaining, you're actually going to take a sample, right, from a population randomly. And at the end of the day, you're going to generalize result on the entire population. Okay, when you generalize result on the entire population, we normally explain at a group level, at an average level. We don't explain at individual level. Does that make sense? So that is average. That's why in statistics, you're actually going to hear average effect all the time. Average this, average that, because we actually seek generalization, inside by averaging over many observations under investigation. But let me tell you this, when you are seeking a predictive goal, we don't do prediction at average level. We do prediction at individual level. You want to predict a new observation, okay? not at average level, but individual level. And let me tell you this, what is going to be gainful to the scientific community? Can we have a way to make a prediction at group level as well? Or can we have a way to explain at individual level? And that is going to be gainful. That's going to be new thing to do. Does that make sense? Okay. Now, what I want, this is very, very important. This is the most important tension that distinguish your intention, like whether you want to explain or you want to predict. I'm going to tell you what is the worst enemy of researchers in the scientific world. Okay, I'm going to tell you right now. I show you this particular equation last week. The mean square error was broken down into that. You remember mean square error, right? Okay. Um, we also call that expected prediction error, which is more or less the difference between the actual observation and the estimated function. Now, I'm going to tell you why this is very, very crucial, and I need you to pay attention now. Now, I'm going to start with the first one. I'm actually going to start with this guy. The variance of y, okay? Even if you specify your model correctly and you estimate parameters in the model, okay, appropriately, there's always going to be variance of y. There's always going to be that error. Does that make sense? That error is part of model, the variance of y, the variance of the response. The moment there's a variation in the response variable, there's always going to be an error associated with that. Whether if you correctly specify your model, if you estimate your parameter adequately, you're going to have that error, the first one, in every model, whether you are explaining or you are predicting. Does that make sense? But let me tell you the second one, bias. Bias. Bias it arise as a result of model misspecification. When you misspecify your model, you're actually going to have bias. Maybe you are supposed to use a linear model, okay? Or you use a complicated model, okay? A model specification arise when your model that you specify does not commiserate with reality. Your model doesn't match reality. That's going to be called bias. That will induce bias. And let me tell you this. Bias is the worst enemy of everyone in the scientific community. They want to bring it down. A statistician wants to reduce bias. An economist wants to reduce bias. A psychologist wants to reduce bias. Everyone in the scientific community wants to reduce bias. And let me tell you this, when they are trying, why are they trying to reduce bias? They are trying to reduce bias be, because they want to have what I call adequate representation of their function, the underlying function. That's why they are reducing bias. I'm going to say that again. They reduce bias, okay, for them to have adequate representation of the underlying function. But let me tell you this, when they try to reduce bias, increasing the number of variables in the model, because one way to reduce bias, okay, maybe they're trying to reduce bias because they realize the model is too simple and they're trying to add variables, features into the model. And when they add features into the model, when it is too much, even though they will succeed in decreasing bias, but they will run into another problem that I call high variance. Does that make sense? High variance, high variance, high variance. Okay, high variance is when you have so many variables in your model, you're actually going to experience what I call over parameterization. That will lead to overfit. Your model will overfit. Your model is going to overfit. Initially, the model has high bias because it underfit. They believe the model is too simple and they continue to add features. And when they add features, even though they succeeded in minimizing bias, but they created another problem of high variance. And if you take a look at this guy, it is the error that you commit using sample to estimate function, because you're going to use sample of data to estimate the function. Since you are estimating, there's going to be an error in estimation. There's always going to be error in estimation. We can never have a situation whereby an estimator is the same thing as parameter. No. We normally, you can't have, if this guy is an estimator and this is a parameter, we don't have this kind of situation using a sample. But what we normally have, we can say on average, expected value of an estimator equal to parameter, which we make a theta cap to be an unbiased estimator. So if I want to talk about bias right now, it's going to be the difference between this guy and this guy. It could be if it is zero, if the difference is zero, bias equal to zero. If the difference can be negative or positive, and that is where you can see a square, right? A square indicate we're actually focusing on the magnitude. Okay, now let me now let me now tell you the difference between when you are pursuing an explanatory goal and predictive goal. Let me tell you, those who pursue explanatory goal, they normally reduce bias. But when they reduce bias, what will happen to the variance? The variance is going to be going up. So which means explanatory model, we only have explanatory power, but not a predictive power, because they were able to minimize the bias, but they are not able to minimize the variance. Okay? So the only benefit is theoretical accuracy. That is a benefit for them. Theoretical accuracy in terms of explanation, but they will actually suffer a penalty. And that very penalty is predictive accuracy. Explanatory accuracy does not translate into predictive accuracy. But do you know what the machine learning experts, on the other hand, those who seek predictive goal, will minimize the combination of the bias and variance. There's a benefit, there's a penalty. I'm going to tell you the penalty now. Where you try to minimize bias and variance, okay, the penalty is you're going to sacrifice the truth. You're going to sacrifice theoretical accuracy for improved empirical precision. Does that make sense? So one way or the other, the two, they are sacrificing something. Okay, and that is why we need a trade-off between a bias and the variance. Does that make sense? That's why we need a trade-off. Now I want to go into model fitness and model complexity, and I need you to pay attention here. When I'm talking about model fitness, I actually want to assess how the estimated function matches the observations, the data. I'm going to say that again. Model fitness. We really want to know. That's what we do in statistics. You take a sample size of n, and after taking a sample size of n, you actually estimate a function, and you now want to assess how does this function matches my data set, the data set that you use. In model fitness, the criteria that we use in model fitness, there are two: sum of square error sum of square error, and R squared. Sum of square error and R squares are the metric of evaluation for model fitness. In model fitness, you are actually using model explanation where you use all your data, all the sample. You did not split. Okay? Now you actually estimated the model and you compute the sum of square error. The sum of square error is the square of the distance between the actual response and the predicted response. You sum it together. That's sum of square error. And you also base it on R squared. R squared is called its coefficient of determination. The coefficient of determination actually measure the percentage of variation in the response the model can explain. Okay, look at that. Percentage of variation in the response the model can explain, which means you are not doing prediction, you are explaining. So the metric of evaluation for model fitness is sum of square error and the R square. Now, but there's an issue. When your model is becoming complex, right? You have a multiple linear regression where you have so many independent variables, okay? You cannot trust your R square anymore. Can somebody tell me why is it that I can't trust my R squared when if I have so many features? Can somebody tell me why is it that I can no longer trust R squared as a measure of complexity? Even though I trust R squared as a measure of fitness, but for complexity, I can no longer trust R squared. Why? Can somebody tell me? Okay. Oh, go ahead. Okay. Overfitting. Okay. Now, are you very close? What happened is this. If I continue to add independent variable into my model, even if the independent variable that I'm adding doesn't make sense, R square will be going up. Does that make sense? You know, if I have a linear regression, if I have, for instance, if I have a linear regression, okay, if I have a linear regression, if I increase to this, and I also increase, if I continue to increase, or let me just say x1, x2, um, um, plus s2, this, okay? Now, the R square here is going to be bigger than this one. The R square here will be the biggest. Even though if this variable doesn't make sense, R square is going to go up. Okay, R square is sensitive to addition of variable, even if the variable doesn't make sense. And you know what we normally, a module with higher values of R square, we normally say is the best module. But in a situation where the variables, I have so many variables, having so many variables is what we call complexity. Therefore, R squared cannot be trusted as a criteria for model complexity. And what do we use? So if I need a criteria of evaluation for model fitness and model complexity, then I'm not going to use R square, but I'm going to modify them. Okay. And I'm then modifying R square, I'm actually going to have adjusted R squared. Has anybody heard about adjusted R squared? Okay, adjusted R square is a metric of evaluation for model fitness and model complexity. Then I can no longer use sum of square error because let me tell you this. If I continue to increase the variable in my model, even if the variable that I'm adding is nonsense, the sum of square error is going to be going down. And of course, a model with the lowest sum of square error is a good model, is the best model. Okay, but we cannot trust some of our sum of square error in when we have a module complexity. And what do we need to do? Then we need to modify sum of square error. And what do we do? Then modifying sum of square error, we're actually going to have AIC and BIC. Has anybody heard about AIC and BIC? Now, what I'm trying to say right now, the criteria for module fitness, we use sum of square error, R squared. The criteria for module fitness and module complexity, we use adjusted R squared, AIC, and the BIC. The module with the smallest AIC or BIC is the best. The module with the higher value of adjusted R squared is the best. Now, all of these, they are for module explanation. They are not for module prediction. Or what I've discussed so far, whether module fitness or module fitness and module complexity, I'm only focusing on explanation. If I'm seeking an explanatory goal, I'm not seeking predictive goal. If I'm seeking predictive goal, I will use a different metric of evaluation. And let me tell you if you are seeking a predictive goal, okay, if you are seeking a predictive goal, the metric of evaluations for prediction, number one, mean square error, root mean square error, mean absolute error. Those are the metric of evaluation for prediction with a cross validation. Does that make sense? Now, when you are into module explanation, please take notes. We don't split our data. When your intention is to what? Is to explain. We don't split our data. Because you need the whole data. The larger your sample, the better for explanation. Does that make sense? But for prediction, we don't use the whole data. That is where we split. We split into training, into test. Now I want to go into now what we want to do next. We actually want to focus on prediction. And when we are focusing on prediction, how can we assess our model? I think I've already uploaded the material for Wednesday and Friday. You can check Canvas. Now, the cross validation is actually one of the criteria for model prediction. Now, let me tell you this. When you are into prediction, we don't test hypotheses. You don't need p-values. P-values for what? But when you are doing module explanation, where you're going to make use of all the criteria that I mentioned before, okay, you need p-value. You need p-value, don't forget. When you are seeking an explanatory goal, you want to test a causal hypothesis, which means you want to know the effect of a particular variable on another variable. And if you want to know the effect, you need to conduct a t-test, particularly when you are working with a linear regression. Okay, maybe you're looking at the effect of, just like what I work on in my bachelor project, I work on effects of inflation rate, exchange rate, and consumer price index on the GDP of Nigeria, which means I actually use a multiple linear regression. In that research, I'm not interested in prediction. My interest was on explanation. I actually want to isolate the contribution of exchange rate to GDP, the contribution of consumer price index to GDP, the contribution of inflation to GDP. Now, in that situation, I need to use all my data. I don't need to split. And I will have a p-value associated with the regression parameter associated with a particular independent variable. where I'll be able to look at the p-value and compare the p-value with the level of significance. If the p-value is less than a given level of significance, preferably 5% standard, we're actually going to say the corresponding predictor is significant. All of that is going to come up when you are seeking explanatory goal, not predictive goal. But in seeking predictive goal, of course, you're actually going to see us talking about some other metric of evaluation, like mean square error. Mean square error and root mean square error, if your focus is on prediction. But if your focus is on classification, we're going to talk about misclassification error. Misclassification error. And all is going to play out in the next lecture. So what I've given you today is for you not to use a wrong way of assessing your model. If you use a wrong way of assessing your model, then that will not give you the clear picture of how adequate is your model, because you are using the wrong. It's like somebody who seek justice in a wrong court. And that's why at times it's going to look as if our models are failing us. Our models are not failing us. We are the one that we're not doing the right thing. Okay, Judge Box said, and I quote, all models are wrong, but some are useful. But I said, okay, all models are wrong, but we can make some to be safe and useful. How? Number one, by using an appropriate metric of evaluation. And how are you going to know? Then you need to be able to tell the world what your intention is. Do you want to explain or you want to predict? If you want to explain, of course, you're actually going to use explanatory model. If you want to make a prediction, it is going to be a predictive model. And let me tell you this: explanatory goal does not translate into predictive goal. Let me tell you this: when you are seeking a prediction or a predictive goal, there is possibility that you are likely going to use flexible models. I told you the other time, the flexible models, okay, when a model is too flexible, it's actually going to suffer interpretation issue. There's going to be an interpretation issue. But let me tell you the good news. Statistical explanatory model, okay, statistical explanatory model, okay, there's a lot of transparency. Everybody knows the mathematics around conducting t-test, conducting p-value, all of that. There's a lot of transparency because of mathematical knowledge. And because of that, you can interpret. Okay, there's no interpretation issue. But the models that are interpretable may not do the work of a predictive, may not have a very old predictive power. Okay, now let me tell you this. A variable may be significant in a model. Quote me anywhere in the world. A variable may be significant in the model. It's significant in a model for explanation. Okay, that same variable may not necessarily contribute to the best prediction. We normally do this. When a variable is not significant in a model, we normally discard it, right? That variable may is not significant for explanation, but that variable that you exclude may be significant for prediction. The same variable. There are some study, particularly if you're looking at a risk factor for lung disease, risk factor for lung disease. There's a particular variable that must be included as a factor, even if the variable is not significant. That variable is smoking. Even though it's not significant, it's going to be in the model for lung disease. Okay, so when you discard a variable, believing that it's not statistically significant because of the p-value associated with that regression coefficient, it's less than 5%. I'm sorry, it's greater than 5%. The p-value is greater than 5%, and you realize that it's not significant, and you discard. You only discard excluding that from your model is good for model explanation. But for prediction, we don't care about removing all of that. We need a combination. That's why in big data, you see a lot of features that are used at the same time, and at the end of the day, that give them the best prediction. So the most important thing is ask yourself, what is your intention like? I'm going to share the information about my talk. My talk is going to be on February 5 at 4 or I'm going to share that information. That very talk is very, very crucial because I'm actually trying to balance interpretability with predictive ability in a model. Can we have a model that we're actually going to be a mixture of predictive, like I want to retain predictive ability and also want to retain interpretability at the same time. I want to go hybrid. Going hybrid means I'm actually using a combination of statistical method and machine learning algorithm in the same model. Is there any question before I go today? Is there any question? Make sure you all stay safe and have a lovely day. Bye for now, everyone.
Thank you.
You're welcome.